In this video, I will be describing a topic of linear algebra that might be deemed as one of the most intimidating or abstract, mathematically abstract topics, um, vector spaces, and several concepts that come with it. But I will try to make it such that it finds itself in the whole understanding of the data science, how we make use of matrices and vectors in data science. And thereby, I would like to, I hope that I will be able to convey the concept of dimensionality in matrices. Before I start, so I have a few notes here that I will share. Before I start, I would like to start with mentioning, let's remember how we make use of matrices. So we know that matrices can be our data points, right? They can be the columns of which or rows of which can be different data points that we will process. Or alternatively, they are operations, linear operations in neural nets that we typically use, or sometimes very recently, they can be matrices can hold similarities between different vectors and what we're going to call attention matrices. And all of these operations, all of these things that are represented with matrices will have to be described with some of the important mathematical definitions. So some of these definitions are you see I will cover um, that are going to go all the way to dimensionality, because I think dimensionality, the space, how the space exists, is the most important thing when we are talking about from the data science perspective. But um, let's like I will get to that, but let's start by questioning what is the dimensionality of the data. You think something that we think might not actually be the actual answer of dimensionality. So let's take the most boring data set, the iris data set. Iris data set that you see on the left. There are 150 measurements of some flowers, and there are 4 columns. Each row is a sample, and each column is talking about a future of this data point. So sepal length, sepal width, petal length, petal width. It's talking about, it's describing the future of this flower, right? So you can think of this data samples are coming, they are described with 4 different dimensions, right? So so far we were able to build an intuition in which our data points can be described with multiple dimensions, and we can deem them as points in a space. And then you can think that since we're observing 4 features, each sample for each sample, then the dimensionality could be 4, but maybe not, right? So the dimensionality is a little bit more involved than that. But before I move on to dimensionality, I think we need to visit an understanding of a vector space, right? So I will, since I am, since this course is from University of Chicago, of course, the example I'm going to provide is going to be from the God himself, um, Michael Jordan. So look at this image, and that's a data point. So this data point, this image, has some dimensionality. I don't know yet. That's something that I am trying to understand. The dimensionality of this image of Michael Jordan, however many pixels are there in the image and colors, right? So it's going to make each pixel is going to be represented with some colors, right? So it is going to make me make this image a point in a space, right? So like, of course, I cannot represent like no one can. We live in a three-dimensional world. I cannot draw a 4D object on uh, on a screen. I did not even draw a three-dimensional space. It's an illusion. It's a two-dimensional. The screen that you're looking at is actually two-dimensional. So I actually it's an illusion of three-dimensional space. Anyhow, so let's imagine that my picture of Michael Jordan dribbling is a point on that megapixel dimensional space, right? So it's here. And also we can argue that another image, a very depressing image from my childhood, Mufasa's death from Lion King, is also an image. It's coming from some number of pixels, and it's also exists in this vector space. Let's trying to understand a, 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 a a space of points that make up images. If I'm interested in processing images, if I'm doing computer vision, uh, I would like to be processing these data points in that space. So like these data points make sense, should make sense, such that if I am, let's say, if I'm taking another picture of Michael Jordan, it should be close to the first image. So like, and just like data points, when we are, or like points in a space, when we're trying to navigate from one place to another, the proximity should also exist. So that said, then I can introduce the mathematical definition of a vector space. So a vector space from the linear algebra perspective is a set of vectors. All of these vectors are my data points, my images, my audio, my sentences, whatever, but um, from the linear algebra mathematical perspective, a vector space is a set of vectors, right? And all of these vectors are closed under linear combinations. So, um, so I'm talking about a space. So the closed means for any two vectors, if I take any images in that space, um, V and W, that means AV plus BW is also going to be um, in that vector space. So vector space does not necessarily, in that definition, does not necessarily talk about the collection of points of my data set. It's kind of describing the space that my data points live on, and they conform to linear combination operations. So for example, very simply, R square, R cube, that are vector spaces, two-dimensional, three-dimensional, four-dimensional, and several dimensional spaces can be vector spaces. Or they don't need to be like we covered recently, and we will see today that that they don't necessarily need to be cubes or planes or lines. So we're going to get to definition of vector spaces. But from the vector spaces, we also figured we a few videos ago, we tried to find from this video vector space set of points that can be made with using a linear combinations of some vectors, remember? So when we were talking about that, then maybe we can argue, going back to let me go back to this slide, going back to our Michael Jordan and Mufasa's that scene and another Michael Jordan. If we think about all of the images that live on this world, we can talk about, we can also understand that some points of this world that are images are not populated with actual understandable images. For example, take a point that has all black colors, right? Like all zeros, for example, that's not necessarily going to give me a meaningful image. Although, like, strictly speaking, vector spaces should have all zeros. That was maybe an unlucky choice from my end. But take an image that's all white, right? It's not going to be on my data set. So we can actually talk about a subspace of that space on which my data set is going to live. So, which brings us to the concept of subspace. So this we can understand this. Images are on a like um, very big, actually too big and redundant space, because we have to do something for every pixel there. But not all combinations of the colors of these pixels exist in a natural image or natural language or something that can be represented and understandable by human. Therefore, we come to an understanding of a subspace. So subspace is going to be important to describe um, data sets that live on an otherwise bigger space, vector space. So for example, in this example, you see this image data set. An image data set, samples of this, samples from this image data set, they will all become points on this huge space, vector space, but they're not going to be everywhere. So remember our little plane of or hyperplane for that matter, region within that big space that can accommodate my data points of interest. Therefore, then I can talk about a subspace of a vector space, um, which is defined is another vector space. So a subspace is also another vector space, but that's contained another inside another vector space. So example of subspaces, for example, let's take the vector space R cubed, and the subspaces of this vector space is any plane, any line um, that that's going through the zero vector from that space. So that was our subspace definition.